Thank you for joining us today for this third webinar about energy flexibility. We will have a specific focus today on how energy flexibility can be key in supporting industrials, energy-intensive industries in achieving their low carbon, their decarbonization strategies. So today we will hear two presentations from speakers from Energy Pool. We will start first with Edouard. So Edouard is a director of the enablement program at Energy Pool. He will present us the active factory program and especially the value creation of advanced smart control and electrification. We will keep up then with Romain. Romain is a R&D engineer and energy economist. Romain will give us a global overview of decarbonization and key figures about it, of course. And finally, he will make a focus on new flexible assets such as batteries, electric vehicle, and hydrogen. We will close this webinar with a 15-minute Q&A session. So please use the chat window on top of your screen to send your questions to our speakers. We will start with a brief introduction about Energy Pool. So Energy Pool is a smart energy manager of complex systems. We cover today activities such as demand response aggregation, which is our historical, okay, should be fine. So we cover today activities such as demand response aggregation, which is our historical core business, consisting in monetizing electricity flexibility flexibility in electricity consumption, from CNI end users. And today, in addition to demand side, we also manage and optimize many other distributed energy resources, such as batteries and microgrids, for example. We did start our activity about 10 years ago in France, back in 2009. And today we are developing business activities in around 10 countries, including Malaysia, Thailand. We as energy transition enabler, we address key needs from energy market players through consulting, technology, and operation management services. Well, that's all for this quick introduction. I will now ask Romain. Please, Romain, the floor is yours.
Thanks, Laura. Hello, everybody. Thanks for attending this webinar. So today I will just make a quick introduction in this topic about decarbonization. What is decarbonization, and how is it a need both for climate and also for businesses? So just to give you some big figures, the total global emissions in the world were in 2018 were 33.5 gigaton of CO2. Data from the IEA, in which 6 gigatons, so roughly 18%, come directly from the industry, and more than that, 14 gigatons, roughly 40%, come directly from electricity and heat generation, so the power sector mainly. And so if you look at the graph, at the chart on the right, the global emissions must fall by 7.6% per year each year until at least 2030 to keep an hope to meet the plus 1.5 degree scenario, in which what is the target from the Paris Agreement. And so to give you an example, it is assessed that the COVID-19 lockdowns in 2020 caused a unique 7% loss this year. So just to give you an idea, we would need the equivalent of one more COVID-19 each year to meet this target. So what it means is that it's not the solution as it is, but in fact structural changes will have to be made to meet this target. And one of these is the decarbonization. So one thing is that here we talked about the need for climate, but also the decarbonization is also a need for businesses. Why? Because there is some threats on businesses from the carbon constraints, and we can see it through different initiatives coming into place in the world. For example, the three I listed there. The first being some different carbon pricing schemes appearing all around the world. For example, in the European Union, it's a trading system of emissions quota. So to give a price on carbon. There are also carbon taxes in different countries such as Japan, Australia. In the US, there is also another carbon pricing scheme. The European Union has also put in place is currently putting in place what they call a carbon border adjustment mechanism. So it's roughly a border tax on carbon emissions from imported goods. So this could be some restrictions to enter the European market. And another point is the London Metal Exchange, the LME, so the main trading place for the main exchange for metals such as aluminium, for example. They have put in place a trading platform for specifically low carbon aluminium, so to differentiate it from normal, I would say normal aluminium, which could be quite emissive. And just to meet the demand for low carbon aluminium. And so what it means that being a carbon intensive industry in this context, and it is a growing situation, being a carbon intensive industry could soon be a huge business risk, in fact, because you may face, if you are a carbon intensive industry, you may face some market access restrictions for different markets, and often big markets such as the EU or the US, for example. But also you could, I would say, simply lose competitiveness because your products could be more expensive than local, I would say, local products. So, for example, from the carbon border adjustment mechanism in Europe. So let's move to the next to the next slide. Make just a focus on the ASEAN region. So just to give some big figures, the electricity and heat and industry sectors highly contribute to the area's emissions. So both contribute for like roughly 63%. So almost 2/3 of the emissions of the ASEAN region. And in this, carbon-intensive sources account for like 77% of the electricity generation. So more than 3/4 of the electricity generation comes from carbon-intensive sources. But there is a hope to decarbonize massively the electricity in the ASEAN. It's from the Plan of Action and Energy Cooperation from the ASEAN, so the APAEC. Phase 2, so starting this year until 2025, with different objectives, but the three main I identified were reducing by 32% the energy intensity from 2005 basis. So just improving the efficiency, the energy efficiency of the industry. 23% reaching a 23% of renewable energy in the total primary energy supply. So this not includes only electricity, but also all the energy sources. For example, like transportation also. So we will have to electrify a lot of uses to help meet this goal, because it's more easier to deploy solar PV and wind than converting finding new solutions, new alternatives to petroleum, for example. So electrification would be a key to replace this energy consumption. And then 35% of the renewable energy in the ASEAN's installed power capacity must be 35% of the installed power capacity in the ASEAN should be renewable energy. It is 25%. It was 25% in 2018. And so when accounting from the global growth of installed capacity, it would mean doubling the renewable energy capacities. So roughly plus 66 gigawatts more of renewable energy. So it will pose it would cause a huge issue on power grids, and so this needs I would say a solution. And just to give another big figure, in the East Asia and Pacific area, the industry accounts for roughly 1/3 of the GDP. So all those topics I exposed here by talking about the objective, etc. It is big stakes that must be accounted for in the energy transition, because it could impact strongly the industry. So just to summarize what has been done, what has been said, there is a big objective, there is a big goal of meeting the carbon neutrality target by 2050. And to do this, we will focus on three main. The world will focus on three main topics, which could be electrification and decarbonization, renewable growth, and also deploying new energy systems, such as, for example, microgrids, storage assets, hydrogen, etc., etc. But so those three new items may cause different big issues on the power systems and on the energy transition. Some issues that need to be addressed, such as peak demand management, an increase in the electricity cost, some generation that could be less dispatchable with a huge part of renewables, higher network contingency, and overall the economic optimization and the central question of profitability of power systems. So just to say there will be an increased need for flexibility and for a smarter energy management. And that's the good point, because at Energy Pool we can provide a lot of consulting and support on flexibility and smart energy management. What is roughly flexibility, demand flexibility? We can operate industrial consumers with their agreement, of course. Operate industrial consumers to reduce or increase their consumption at times the power system may need it, in front of a corresponding remuneration to provide those services to the grid. And so we will expose in the rest of this presentation some solutions, some ideas to help the industries participate in those flexibility schemes with the power system. I will now let the floor to Edouard to present you the Active Factory program. Thank you.
Hi everyone. So yes, indeed, what is this Active Factory program? Well, basically a bit of context, just on the next slide, please. So, well, sometimes as a factory, you might be stuck between two things. Let's say the first thing is the energy markets or contracts, which are becoming more and more complex and volatile, especially in Europe, but it's starting to occur in several countries in the ASEAN place. And also, as Roman just mentioned, you might have some sustainability objectives uh, target internally to actually to improve your competitiveness and to be more resilient in terms of CO2 footprints. And we believe that those two constraints can be combined, especially in investing on flexibilization. So obviously, as Energy Pool, our know-how is the flexibility, and we believe that this flexibility has a great value for the community on the power grid and especially on the decarbonization. Sorry. So indeed, if you flexibilize your process or your factory, you might create resilience to the different markets, energy markets, but also it gives you the opportunity to modernize your installation, and we will give you some examples, especially on electrification or new smart control and etc. And as I said before, improve the competitiveness to be a step before the big wave regarding decarbonization, which is coming. Also, it's give you the opportunity to speed up your energy transition, especially on renewables or also hydrogen potentially, or other brand new topics which are coming on the industrial field. And depending on your country mix, but your flexibility do have a value for the grid, especially on different reserves, and it is on reserves, but also on energy wholesale market. So on the next slide, it's simply to present you the value proposition of this active factory program is to first of all go along with the energy intensive industry, so primary industries and transformation industries, but potentially not only. And the plan is to invest on this on this flexibilization. So sometimes people are a bit need some support regarding the different questions here. So what is the actual real potential of your flexibility on site on a given sector? So from cement to steel factory or aluminium factories and etc. What is the actual potential? What should be the the right target in terms of the different phases to go from a first step, only perhaps 2-5% of flexibility towards a big step from electrification of parts of the process, or even a fuel substitution from your gas boiler or whatever. So this is all the strategical path, which might be a bit difficult to assess at the first start. And then finally, it's how to finance that. So it can be quite small investment towards a big investment. For instance, replacing rectifiers on an aluminium factories might be a few million euros, and on the contrary, I don't know, using some new smart control might be only few kilo euros investment. So the active factory value proposition or service is basically to collaborate with the industries to define, finance, and implement all this strategy, which at the end must be and is profitable overall. So this is the main thing here that we want to push. So yeah, here is just to give you an artist's view of what we believe that needs to be done is to actually have a mapping of the different. So we do have internally a mapping of the different technologies, and depending on capex and values in the future, we are able to propose, depending on the factory environment and maturity, to propose different ways towards the final energy transition. So it's basically the main approach of the active factories. So we are first focusing on quick wins. So for instance, as I said before, smart control, and then perhaps look at the storage or the power to gas, and obviously all on the strategical path you can gain from the combination effects of those different technologies. So, and of course, so it's not purely profitability, but you have also lots of non-quantitative benefits, as public renown and etc. regarding the CO2 footprint that you might have on the country, especially. Next slide, please. So yeah, just a summary of what I just said is indeed that your active energy, so in terms of especially electricity, so has a great value for the community. So you can transform. Usually, a factory is made to have a quite stable, flat consumption. But actually, if you force to have it active, so fluctuating, it has a great value. And we are trying to make the most of the latent flexibility. So we, from our experience on different factories, there is lots of flexibility not used currently. And yeah, as we mentioned, the energy transition is a good way to participate in the power system stability. So just few figures regarding European flexibility value, which might be not yet the case in ASEAN area, but will be soon. We do hope is the different reserve bring lots of value in terms of monetization to the grid, and it's valorized when you provide your flexibility on the grid, and this is our core business as energy pool. The wholesale markets also can give good revenues from the spread of gas, electricity, and so on. So the simple step is to invest together, to do a shared BP, collaborate on the business plan, and do all the EPCI, energy engineering, procurement, and commissioning on site together, and then provide long-term operation to the grid of this flexibility on the different opportunities. So first of all, the grid system, but also the CO2 reduction. So yeah, so here is the business case that we currently have internally in Europe, in a country in Europe. So it's a big aluminium smelter, so close to 150 megawatts consumption. So, and we are currently having a first step of flexibilization of the rectifier control. So we have on site 10 rectifiers providing roughly 40 kilograms each, and we are installing and preparing all the instrumentation and the smart control of those rectifiers in order to release flexibility. And we had first a big block of emergency power, more than 100 megawatts, and 10 megawatts of real-time flexibility, new flexibility provided to the grid. And so it's a first step indeed for the factory towards a further modernization of the on-site power system and integration of especially solar PVs on the roof. And in terms of BP, just few figures. So it's not a huge amount of investment, firstly. So it's 500,000 investment regarding smart control, but the payback period is actually 1 year and a bit more because of the COVID period. But it's roughly the figures of that approach. So this is an example of revamping the existing. A second example is, Laura, please. Well, Roman, also a second example is fuel substitution, or let's say in that example, electrification. So Roman, if you want to do a bit of context.
Yeah. Just a bit of context. I will give some big figures on electrification, thanks to an excellent report from McKinsey Consulting. So just to give you some big figures, the world industrial energy consumption in 2017 was a bit like that. Roughly 20% from pure electricity consumption because of electrical components needed. 35% of fuel consumption, such as gas, oil, or coal, as a feedstock. So directly to use it in the process as a material, and then around 44% is fuel used for energy. So burning coal, burning gas, burning oil, just to produce energy. And so this part could be theoretically could be electrified. And how and why? If we look at what are the components of those 44%, you can see it on the right hand chart, and you can see it is composed by mostly low to high temperature heat uses. So just to produce hot water, or up to melting glass, or hot strip mills, or limestone calcination, etc., etc. So there is a lot of use of fuel for energy, but mainly for high temperature. And what we say here, and what McKinsey Consulting says in this report, is that half of it, around roughly half of it, could be easily electrified by now. So low to high temperature heat is already commercially viable if you want to electrify it. There is existing technology that are perfectly commercially viable. And on top of that, roughly a third of it only needs to step up existing technologies. So for example, if you look at glass furnace melting, or reheating in hot strip mills, there exists some new technologies that are in R&D, or even on pilot phase, that are trying to electrify this energy need, just to produce the same heat with electricity instead of fossil fuels. So those uses could be more or less easily electrified. But why isn't it done if it's so easy? Because there is some main breaks against some massive electrification. The first could be the high price of power, and also the low cost of carbon. If you don't have a high carbon price, or even a carbon pricing system in the country, the carbon does not have a cost. So burning fossil fuels instead of electricity does not have an impact. There is also issues on the power generation emission, because if you look at the power system, and it's at least as much emissive as your industry, there is no strict interest of electrifying the system. And also there can be issues on the power grid's reliability. So in countries in which the power grid is not so much reliable, you could not want to electrify because you cannot rely perfectly on the grid, and at least with fossil fuel you are secure that you will always have energy when you want it. But there is solutions to that. There is solutions. For example, if you account on renewables energy PPAs, power purchase agreements, they can reduce your electricity cost because in most situations they cost less than the fossil fuel, and so you can reduce you can reduce your bills by contracting some renewable energy PPAs. Another topic is that about the emissions, the renewable energy provide low carbon electricity. So if you consume electricity from a renewable energy sources, you will have low carbon electricity. So then the emissions from electrification would not be as much as you would expect. It would not be the emissions from the power system. It would be emissions from your low carbon electricity. And so in this situation, the scope 2 emissions from electricity would not be that high. And concerning the power grid's reliability, just a last topic is that the demand response flexibility must participate in schemes like that. So if you input a lot of renewable energy in your mix and use it to provide industrial consumption for electrification, you must, in the other hand, you must participate in demand response flexibility scheme, and the power system operator must put in place some demand response flexibility scheme to account for the new risk of grid management from renewables. So this is an approach in which renewable energy and flexibility must come hand in hand to accompany the massive electrification of industry, thus its electrification and decarbonization. So I will let back the talk to Edward to explain this business case.
Yes, thank you. So indeed, here is an example of a business case that on which we are working out currently on electrification. So it's a large steel factory. So the project going on is to electrify a rating furnace. So this big furnace before, so rating what we call bloom, rating the steel before drawing, before hot drawing. So this furnace is currently so it's a quite a long one, and it's more than 50 meters furnace, and with close to 40 burners of gas. And the first plan of the main project is to electrify one zone of this furnace. So it's to replace 7 megawatt of gas with 6 megawatt electric. So giving this opportunity to also have hybridization between gas and electricity, in order to arbitrate between gas price and electricity price and etc. So this obviously the 6 megawatt, the new electricity potential can be used in order to provide heat to the steel bloom, but because of the inertia of the whole furnace, and because all the fumes are going through the furnace also, so we'll be able to play with the electrical flexibility from real time to longer energy provision. And this overall flexibility electrification project provide a bit more than 5 kilotons of CO2, which is really not nothing in regarding the actual emissions of the overall factory. So this is quite a big project going on. So with quite a big capex, so between 2 and 3 million euros. So we are looking for subsidies currently, so on this project, and but the overall flexibility revenue that we will gain from the grid mechanisms and also the CO2 reductions, it gives us a payback or break-even period of 5 years, which is a bit too long for the industrial, because usually those industries are close to 2 to 3 years return of investment projects. Higher period is a bit more complex for them. So it's the bringing the flexibility within the BP is actually giving the opportunity to the site to do a longer project in payback period. So below you have a small a picture also of the engineering going on. So it's a real picture of the a real project, AutoCAD project of the site. So integrating some heating elements within the zone and doing all the electrical infrastructure, gradiators, thyristor, and etc. control of this, and obviously the upstream transformers. If you can go, sorry, to the next slide. So, and here the third focus is, so you remember we first look at the revamping the existing. So for instance, new control system and etc. Well, using the existing, then doing new things in terms of process, so fuel substitution, electrification, and etc. So it was our second focus. And the last one in terms of active factory program is to actually provide a new flexible asset. So provide batteries, new storage, new hydrogen, electrolysis, and etc. So I let Romain go through that slide.
Yeah, thanks, Edward. So as Edward said, we will focus here on in this last focus. We will analyze the three main new flexible assets that are trending by now, such as batteries, electrical vehicle to grid, and hydrogen electrolysis. So we will start by giving some key figures for each of them, and then their qualities and main issues. So just to focus on batteries first. So the main figures. If you look at the International Energy Agency forecast, they expect by like 5,500 gigawatt of batteries by 2040 in the world. By now we are just like, if I remember correctly, we are like no more than 10 gigawatt by end of 2019. Sorry. If you look at costs, it's a battery, an electricity storage battery, costs around $300 to $400 per kilowatt hour, and not megawatt hour, kilowatt hour of electricity storage. So the most expensive in the battery is the storage capacity, not the power capacity. And also, if there is some project that are by now considered as a giant project. I will give the example of the Tesla mega battery in Australia. It's like 100 megawatts and 400 megawatt hours. So a 4-hour characteristic duration. So the main qualities about batteries is that they are quite easy to operate. There needs some algorithms, but it's quite easy to operate, and it can participate in different services for the grid, such as, for example, frequency control, peak shaving solutions, and also if you put it, I would say, behind the meter in an industrial site, it could help you better manage your electricity bill by not consuming at peak if there is some critical peak pricing or schemes like that. But the main issues from batteries, it's as I said, the high cost per megawatt hour, the high cost of storage capacity. Thus, it is not really well suited for long needs. For example, if you need some discharge generation for more than 4 or 10 hours, it would not be the most suited solution, mostly because of economic constraints, but also because of the fact that batteries are not designed to provide that much energy in the energy production. Also, it's highly lithium intensive, and it's an environmental constraint that must be taken into account. The second new flexible asset we wanted to focus on was the electric vehicles and the solution of vehicle to grid. So just to give key figures, you can expect around 20 up to 100 kilowatt hours per electric vehicle. So 20, it's a small car. 100 kilowatt hours is the biggest Tesla model, for example. Electric vehicles accounts for roughly 1% of the global car stock by now. It is expected to grow, obviously, but by now it's I would say only roughly 1%, and it represents around 5 million battery electric vehicles in the world. Just to give some figures about the impact of electric vehicles on the power grid, each station could go up to 250 kilowatt per station, per charging point. So if you consider, for example, like Tesla superchargers areas, it could easily go up to a few megawatt per charging area. The main qualities of electric vehicles is that it could help decarbonize mobility. So the main stake is that the electricity to supply the electric vehicle is not more carbon emissive than the fuel used in the cars, but if so, it could help decarbonize the mobility. It also can provide grid services. Thanks to the vehicle to grid approach, we can provide some flexibility thanks to electric vehicles batteries. And also another situation is another point is the smart charging. The smart charging to not over solicitate the power grid if there is some difficulties. You can put in place some smart charging infrastructure to charge the battery when the grid is able to support it. The main issues for electric vehicles is that the charge points could require some management system. As I said, if you want to put in place some smart charging to not over solicitate the grid, you will need some management system. Otherwise it could cause some problem on the peak demand. And another thing for the vehicle to grid flexibility availability is that it's mostly present at night because you use your car in the day to go to work, and you go back at home and you plug it into the power grid, and then it is present roughly at the end of the day and at night. So maybe not when the flexibility is most needed. The last asset we wanted to focus on is the hydrogen electrolysis, which is currently the most trending one this year. Just to give some figures, the hydrogen consumption in the world is already quite high because it's used in industrial processes, but it is expected to triple in volume by 2050, thanks to from the IEA forecasts. Another figure is that it consumes, to produce hydrogen from electrolysis, it consumes around 50 megawatt hour per ton of hydrogen produced. So it's not it consumes quite a a lot of electricity. If you produce hydrogen from gas reforming, steam methane reforming, it costs around $1 up to $2 per kilogram of hydrogen. If you do it from hydrogen electrolysis supplied from renewable energy, it could by now with existing business models, it could cost up to $5 up to $10 per kilogram. So it could be quite expensive, but there is way to optimize the business models. So the main quality about hydrogen is that it could help decarbonize the industry, because you can use it, and we will see it on the next slide. You can use it on in the industrial processes instead of fossil fuels. Laura, if you just can go back, please. Yeah, thank you. It can provide, I would say, any grid services. We will see it then with the flexibility abilities of electrolyzers. It can even provide seasonal storage. That could be an issue in some countries in which seasonality is quite high. And it can also provide what is called the sector coupling. So sector coupling is using gas and electricity networks in the same hand. And so the main issue is that, as I said, it's quite power intensive, but it is an issue and a solution because we can use flexibility. There is quite a high cost per megawatt. So here it's the capacity and not the storage that is expensive. It's a quite complex system to put in operation, and there could be some high yield losses. So this is the flexible asset we wanted to focus on today. So on the next slide, I will expose some ideas about the hydrogen. Mainly what we call the what is called the green hydrogen. So hydrogen produced from electrolysis supplied from renewable energy. So Laura, if you can, thank you. So the topic of green hydrogen comes with two main subjects, which is production from one side and industrial consumption in the other side. So we will first focus on the production. And the production, the two main topics are the costs and revenues. So we just in first we will focus on the costs. And the costs of production comes mainly from the electrolyzers investment and the operational expenditures. Also from the operational management, there is some issues on that, and we will see that. And also the cost of power supply, because as I said, it's highly power intensive. So the cost of supply is a big issue for production costs. But in the other hand, we also have revenues, and for those revenues, you can expect different sources of revenues. For example, if you use it for power generation, so you use it back in a fuel cell to produce electricity. You can also use the flexibility of the electrolyzer to provide grid services that could be remunerated. And also, and I would say the main solution to get revenues from green hydrogen is selling it to consumers. And then we will see how hydrogen could be consumed. We will focus on an industrial ecosystem. So there is different opportunities to use hydrogen. The first one we want to focus on is the mobility. So mobility to power hydrogen fueled vehicles, such as trucks, for example. You can decarbonize mobility from trucks thanks to hydrogen in mobility. You can also use it for heating. So instead of burning coal, gas, or oil, you can burn hydrogen, and this could help replace carbon-intensive commodities and the corresponding emissions. Green hydrogen can also be used in industrial processes, and this is the original way hydrogen is currently used in industrial processes. So first, as a feedstock in current processes, for example, for food or refining or ammonia production. But you can also use it to replace emissive processes. And I will give the example of the direct reduction iron. This is a process using hydrogen that could replace the coal coke that is used in the steel industry. And the last solution to use the hydrogen in an industrial ecosystem, I would say, would be as a power asset. And using hydrogen as a power asset could help you get some, I would say, energy storage, because you can store hydrogen, you cannot store easily electricity. It could also help you with power generation, for example, as a backup solution or for self-consumption. And it can also, as we said in production, it can also provide grid services that could be remunerated, or that could be needed at least from the grid. So I was talking about grid services, but you may say what kind of grid services the hydrogen could provide with electrolyzers and fuel cells. I will go back to that. Just to say that, as mentioned here, we at Energy Pool have a wide expertise on all of those topics: operational management, power supply consulting and operations, power generation support, grid services mainly. It's our core business with also energy storage. And the active factory project helps you in those solutions, such as replacing carbon-intensive commodities in heating, and hydrogen to replace emissive processes. So this is the core of the active factory. So just to say a word about the electrolyzers and fuel cells flexibility. Here in this table, we will see some key figures about the flexibility. So the ramp up and ramp down abilities. So you can see, for example, for the proton exchange membranes electrolyzers, the flexibility, the ramp up and ramp down ability is like 100% of load per second. So it's huge. It's huge. It really means that you can do quite everything you want with hydrogen assets flexibility, and it occurs with current electrolyzers. So alkaline and proton exchange membrane electrolyzers are already in service in the world, and they can already provide any grid services. So being capacity, like peak shaving mechanism, being safety reserve, like less than 15 or 30 minutes services, spinning reserve or frequency control, or even if you want emergency reserve, less than 1 second, you can provide any grid services. And the idea is to get maximum value from that. You need both a grid service remuneration scheme put in place by the system operator and the government, and also a very good smart energy management. And that is what we provide at Energy Pool, to provide this whole ecosystem and complexity management.
Thank you, Romain. Edouard, if you have any word to add, or we can move on to the Q&A session. It's up to you.
Yeah, no, I mean, we can proceed to the question if there are some. Any question from anybody? Okay, so I mean, Laura, so then we can perhaps conclude.
We had one question before the event regarding the first project about revamping and smart control. How long does it take from like the first phase of the study until operations? How many months did you have to work on this project?
Yeah, so as you know, it has been a bit bit difficult this year because of the COVID. But the first plan was to install everything from engineering audit towards the actual operation within 1 year, 1 year and a half. So, and currently we are a bit more at 2 years, unfortunately, because of 6 months. Standby period. But from the very beginning of the contracting and etc., it's 1 year, 1 year and a half. So and the real work, engineering work, is close to 8 months. Especially because there is a big work of because the current installation is quite old. So part of the rectifier system is from the 60s. Another part is from the 80s. So the biggest works was to provide a proper plan to not to revamp everything, but to at a low cost use the existing. So it has been a bit a long process for that.
Okay, thank you. I see that we have one other question from a guest. One about marine mobility. I don't know if Romain or Edouard, are you able to have some information on that? And the other one about does storage affect the overall efficiency of the process? Depends on the process.
If it's about hydrogen, maybe I will take the question, even if unless Edouard, you want to
go ahead.
Yeah. Okay. So about marine mobility, I think okay. So about hydrogen. So about marine mobility, I think the topic is quite the same. I would say there is a difference, obviously, but the idea is quite the same as truck decarbonization. The idea is to power in mobility, in hydrogen-based mobility. The idea is to supply a fuel cell with hydrogen, and this fuel cell will supply electricity to an electrical engine, and so this engine could put into move either a truck or a boat or a train or a car or a lot of things like that. And I would say technically there is no huge difference between trucks and boats. Maybe the main difference is that is on the I would say on the size of the electrolyzer, because in a truck the size could be quite reduced, but in a boat, depending on the size of the boat, but it could be some huge power needs, and so with a huge electrolyzers. But in fact the topic is quite the same. It's just the size that change. The hydrogen production could be quite the same. The effect on decarbonization could be quite the same, because you still compare fuel oil to hydrogen. So I would say the issue would be the same with marine mobility and I would say trucks mobility. The people asking this question was also asking about different types of storage, compressed or liquid. If talking about hydrogen in the storage, and I assume it is, we did not explicitly focused on the storage solutions, but this is something to look at, because just 2 points in that. In industrial hydrogen consumption, mostly the hydrogen is produced where it's used. So the idea is that there is no no big needs of storage if possible. The less expensive of storage is compressed mostly, because if you don't need extremely long periods of storage, the compression, the energy consumption for compressors is not that high compared to liquefying hydrogen, because to liquefy it you have to make it go to extremely low temperature, so it consumes a lot of energy. So mainly storing hydrogen could be better in compressed hydrogen maybe, but that's not the main topic here. The idea is to consume hydrogen as it's produced mostly. And the people asking was also asking about the efficiency on the process. So yes, if you consider power to power hydrogen, I would say, so like power to gas and then gas to power hydrogen, the efficiency is like 60-70% for each phase. So in the end, you just take back 1/3 of the electricity provided in the beginning. So that's why we try to not use hydrogen for power to power, but for industrial uses of hydrogen directly as a feedstock.
Okay, thank you, Romain. Maybe we can conclude and move to the last question. Edouard, would you?
So regarding hydrolysis of waste energy,
Waste energy.
Well, on my side, I'm sorry, I've not actually not many things to provide on that topic. Indeed, yeah, something to look at indeed. But sorry, we are not on that currently.
But this is something on we can investigate or.
Yeah, definitely. Yeah, yes, definitely. Yeah.
Okay. Well, thank you all. I see a question regarding the availability of webinar. They will be soon all available on Energy Pool YouTube channel, so you can watch them. Thank you all for attending this webinar.